Swayam Prabha. Digital India. Educated India.
Welcome to the fourth lecture of the module Spur Gear and Design of Spur Gear. In that, in the lecture 3, we studied the bending stress number or the fatigue bending stress, which was given by this formula where J was the geometry factor, Ko was the overload factor, Ks was the size factor for the bending, Km was load distribution factor or the mounting factor for bending strength, and Kb was rim thickness factor, and Kv dynamic factor or the velocity factor for bending strength. In our third lecture, we studied the overload factor, the size factor, mounting factor or the load distribution factor, and the rim thickness factor. The load distribution factor was determined with the help of this table, where in the first column different sources were given with the type of bearing and the deflection in the shaft and the quality of the gear, and depending on the face width the mounting factor was determined or the load distribution factor was determined. Now it may also be determined by an empirical relation explained in the coming slide. The procedure is applicable to this empirical method is applicable to where the net face width to pinion pitch diameter ratio F divided by dP is less than or equal to 2, gear elements mounted between the bearings, face widths up to 1000 mm, and contact when loaded across the full width of the narrowest member. The load distribution factor under these conditions is currently given by the face load distribution factor CMF, where CMF, which is also equal to Km, is given by 1 plus CMC within the bracket CPF CPM plus CMA multiplied by CE. Now one by one we will study the way these factors are determined: CMC, CPF, CPM, CMA and CE. The CMC, this one, is given by 1 for uncrowned teeth. Uncrowned teeth means the top land is a flat. Now if it is not flat, it is curved like this. Then it is called the crowned. Okay. So for crowned teeth this CMC is 0.8, for uncrowned it is 1. The CPF, this factor, is given by these three formulas based on the face width F. If this is less than or equal to 25.4 mm or 1 inches, then this formula is used, the first one. If the face width is greater than or equal to 25.4 mm but less than or equal to 425 mm, then this second one. And if face width is greater than or equal to 425 mm but less than or equal to 1000 mm, then this third formula will be used to determine the CPF. Now note that the values of F divided by 10 dP, this one, should be less than 0.05. For the lesser values, F divided by 10 dP is equal to 0.05 is to be used. So if F divided by 10 10 dp, dp is the pinion diameter, is less than 0.05, then the value of F divided by 10 dp should be taken as 0.05. Now, the next factor in the Km equation is Cpm, and that should be taken as 1 for straddle mounted pinion with S1 divided by S less than 0.0175. Now, see what is this straddle mounted? We have a shaft here, and this shaft is supported by these two bearings. This and this. The center line of the bearing is given by this center line, and the distance between the bearings is capital S. This is capital S. Now, a gear is mounted on this shaft with center line of face of the gear given by this line, this center line, okay, and the mid span of this shaft is represented by this center line. This is the mid span. Now, the distance of center line of the face of the gear from mid span of the shaft is S1, and the mid span will be S divided by 2 because the length of the span is capital S, so it will be S divided by 2. Well, now based on the value of this S1, which is the distance between center line of the gear face and mid span of the shaft divided by span of the center line of the bearings. So, it may be thought that this is simply a case of simply supported beam. The bearings are in such a way that the shaft is just like a simply supported beam and a load is applied in the radial direction depending on what type of gear is. For the case of spur gear, there will be a radial force. Well, so and this is the center line, mid span. So, straddle mounted means a simply supported type of mounting. So, depending on the value of capital S1 divided by S, if it is less than 0.175, then Cpm is taken as 1, otherwise it will be taken as 1.1 if capital S1 divided by capital S is greater than or equal to 0.707. Now, the CE of that of Km mounting factor is given by 0.8 for gearing adjusted at assembly or compatibility is improved by lapping or both, then it is taken as 0.8, otherwise for all other conditions it is taken as 1. Now, the next factor is CMA of the equation of mounting factor Km. It is given by an empirical formula capital A plus capital B multiplied by face width of the gear plus capital C multiplied by square of face width of the gear, where this A, B and C constants are determined from this table depending on the conditions, like if open gearing is there, then A is given by the first row values. Now, if it is commercial enclosed units, then second row. If it is precision enclosed units, the third one, and if extra precision enclosed gear units, then this one. And this is as per ANSI or AGMA 2101 D04 page 20 to 22. Now, the next factor which is used to modify the Lewis bending equation is the dynamic factor. The dynamic factor accounts for the factor that the load is assumed by a tooth with some degree of impact and that the actual load subjected tooth is higher than the transmitted load alone. The meaning is, while deriving the Lewis bending equation, it was assumed that the load is static, but it is not static. There will be some impact or some, and the gear is moving, so the load is dynamic. And we have studied that when there is contact, then load acts on the gear tooth, and after disengagement till the further engagement, there will not be contact, and so the force is dynamic and the gear is moving, and so there will be effect of dynamic factors. So that is accommodated by multiplying the equation, the basic equation of bending by the dynamic factor Kv. The value of Kv, the velocity factor or Kv factor, dynamic factor, depends on the accuracy of the tooth profile, because if the gear tooth is accurate, then there may not be more variation of the load. The elastic properties of the tooth and the speed with which the gear comes into contact. That means during engagement, the speed by which the gear is coming into contact. So all dynamic effects are taken into consideration in the velocity factor. Now earlier gears were made by casting only, and so the first equation was derived to get the value of velocity factor or the dynamic factor. This was given by 3.05 plus V, where this V is the pitch line velocity. Pitch line velocity V is pi d divided by dn divided by 60, and that will be in mm per second. Well, so later on, with the advent of different other method of making of gears, the other equations were developed. This first equation is called the Bath's equation. Bath's equation. Later on, for cut and or milled profile, the velocity factor is given by 6.1 plus V divided by 6.1. For hobbed or shaped profile, the Kv is 3.56 plus under root V divided by 3.56. For shaved or ground means surface roughness is reduced. So for that case, it is under root 5.56 plus under root pitch line velocity capital V divided by 5.56. Now, in an attempt to account the dynamic effects, AGMA has defined a set of quality number. These numbers define the tolerances for gears of various sizes manufactured to a specified accuracy. Quality numbers 3 to 7 will include most commercial quality gears. Quality numbers 8 to 12 are of precision quality. The AGMA transmission accuracy level number QV could be taken as the same as the quality number. The following equations for the dynamic factor are based on these quality number. The velocity factor Kv is equal to within the bracket capital A plus under root 200 capital V, the pitch line velocity, divided by capital A to the power V, where V is the pitch line velocity in meter per second. The A and B factors are given by these two formulas. Capital A is 50 plus 56 multiplied by within the bracket 1 minus B, and capital B is 0.25 within the bracket 12 minus QV, where QV is the quality value depending on the quality of the gear, to the power 2 divided by 3. Now, this figure shows you the way a dynamic factor Kv can be determined from this figure. knowing the pitch line velocity in meter per second and the quality value or the quality number. These curves are just obtained from this equation. The maximum recommended pitch line velocity for a given quality number is represented by the end point of each QV curve and is given by. That means if quality value is 5, then the maximum value of pitch line velocity this curve can be used is given by VET is equal to capital A plus QV minus 1 whole to the power 2 divided by 200. So, from this formula, the maximum pitch line velocity corresponding to a particular quality value can be determined, these values. Or you can say that this formula gives us the maximum pitch line velocity which can be applied for a particular quality value. So, if quality value or the quality number is 11, then the pitch line velocity may be up to 50 meter per second, but if the quality value is 5, then you can have only 14 or 13 meter per second. For lesser velocity, you can use it. Now, gears in typical machine design would fall into the classes represented by curves 5, 6 or 7, which are for gears made by hobbing or shaping with average to good tooling. So, this 5, 6, 7 is for hobbing or shaping. Okay. If teeth are finish ground or shaved, means good surface finish is made to improve the accuracy of tooth profile and spacing, curve 8, 9, 10 or 11 should be used. So, with the increase in surface finish, the quality value is increasing. Under very special conditions where teeth of high precision are used, in applications where there is little chance of developing external dynamic loads, the shaded area can be used. Shaded area means this shaded area. This shaded area is for very accurate gearing. The gear profile is very accurate, the surface finish is very good, then you may opt this shaded area, and for the shaded area you see the dynamic factor is from 1 to 1.1. So, if you see the transmitted load W and multiplied by the velocity factor Kv, then if very accurate gearing is there, then the maximum value of dynamic factor will be 1.1. So, it will be Wt multiplied by 1.1, it means only 10% increase in transmitted load is there. If you are coming down, then it may be 1.05 or lesser than 1.05. So, very small change in transmitted load is there if the gear is very accurate. But if the gear is not accurate and the quality value is 5 and the pitch line velocity is suppose this one, then the dynamic factor Kv is 1.8. So, in that case Wt will be multiplied by 1.8, and so 80% increase in Wt is there, and this W will be used to determine the bending stress. And so, the bending stress will be very much high or almost 80% high in comparison when the load Wt would have acted on it. Now, if the teeth are cut by form milling, factors lower than those found from curve 5 should be used. Now, the next factor is the idler factor. Idler factor means if the power is transmitted with the help of a pinion and a gear, and when power is transmitted with the help of a pinion and an idler and a gear, then there will be a difference in the load which is acting on the idler and the load which is acting on the pinion and the gear. Because let the pinion is the driver, then it will apply a load, a transmitted load will act on at this location. So when you will draw the free body diagram of the idler, this is rotating in a anti-clockwise direction. So this will rotate in clockwise direction, and so the transmitted load, this is the driven gear, so the transmitted load will act in the direction of rotation of the driven gear, and so Wt will act in this way. Wt, you may say 1, Wt1. Now when you will see this idler and gear, then this will become, idler will become the driving gear and this will become the driven gear. So at this location, the transmitted load will act opposite to the direction of rotation of the driving gear, and driving gear is the idler, it is rotating in this way. So here the transmitted load will act, will be Wt2. Well, so both way the transmitted loads are acting, but in the case of pinion and gear, when there is no any idler, or for this case also, on this pinion only on this side the load is acting, transmitted load is acting, and there is no any other load, only at this point load is acting, but here two-way load is acting. So when if the load versus time graph is plotted, then for the case of this gear and pinion, this pinion and gear, the load will be something like this, one-way load. But for the case of pinion, due to two-way load, the load will be something like this way, this way, this way and this way. Okay. So there will be a load or the movement amplitude, and there will be mean of the movement, and that is 0 for this case, for the case of idler. And range of the load or the range of the movement which is acting will be Mr, which will be from this to this. But when you compare the pinion and gear, then for that case the load is something like this, and so mean amplitude of the load, the bending moment Ma will be this, and the mean will be this one. It means mean stress is acting in this case, but in this case mean stress is 0. So completely reverse type of load is acting. The range of the load or the movement is this one, range of the load is also lesser. So for the case of idler, we have to take care of the different type of load system which is acting in comparison to pinion and the gear. So all idler gear is subjected both to more cycles of stress per unit time and to larger magnitude alternating loads than its nonlinear cousins. So the load factor is taken as 1.42 for an idler, and for the non-idler, means for the pinion and gear, it will be 1. What is the meaning of it? The meaning is, for the case of idler, because it is subjected to more stress amplitude and more range of stress, the actual load, actual transmitted load W will be Wt multiplied by Ki, and Ki is 1.42, and therefore 42% increase in load is made due to this different type of loading system. Now with after studying the all factors which are used to modify the basic bending equation, now we will study the bending fatigue strength of the gear materials. So, gear are made of certain material and it will have some bending fatigue strength. That means it will have some endurance limit, and under fatigue on the gear bending stresses are acting, and so under bending the fatigue bending strength is to be determined. Now, the AGMA bending fatigue strength data, the data which are given by AGMA, American Gear Manufacturers Association, for fatigue strength are all given at 1 into 10 to the power 7 number of cycles of repeated stress rather than 1 into 10 to the power 6 or 5 into 10 to the power 8, because we know that the endurance limit for ferrous material will have a knee. This is the SN diagram, and that means delta sigma divided by 2 rotating beam experiment, and this is number of cycles. So, this is called the SC dash, uncorrected endurance limit. Now, in the materials where there is no knee, and this is correspond to 10 to the power 6 number of cycles. Now, for the materials where there is no knee, the stress amplitude corresponding to 5 into 10 to the power 8 number of cycles are taken as the fatigue strength SF. So, SF dash and SE dash are determined like this, and these datas are for rotating beam. That means for completely reverse load. Completely reverse load means this type of load is there, where the mean stress amplitude sigma mean is 0. Okay. So, for most of the material this type of datas are there, but AGMA has provided the fatigue strength data for 1 into 10 to the power 7 number of cycles. So, the data for fatigue strength are for life 1 into 10 to the power 7 cycles and reliability equal to 99%. If we remember the reliability of this SE dash data, then it was 50%. For SE dash, the reliability is 50%. So, whatever data for SE dash and SF dash is there, the reliability is 50%. But AGMA has given data for gear materials for 99% reliability. So, reliability is 99%, life is 1 into 10 to the power 7 number of cycles, and the temperature is the room temperature. Okay. The corrected formula for the bending fatigue strength of a gear is, so the data, the strength data which we will get from literature will be called SFB dash, and this SFB dash is valid for these conditions. Now, you may design a gear for life other than 1 into 7 number of cycles, or reliability other than 99%, or temperature other than room temperature. So, this SFB dash which you have obtained from AGMA data is to be modified, and this is modified with 3 factors. The first is the KL, which is called the life correction factor. If you want to design your gear for life other than 1 into 10 to the power 7 number of cycles, then this KL is to be used. This SFB dash should be multiplied by KL to get the bending fatigue strength of the material corresponding to this life. Now, if reliability you want other than 99%, then again you have to use this reliability correction factor KR. If temperature is different than room temperature, then you have to use this KT, the temperature correction factor. Now, where KL is the life factor, KT is the temperature factor, and KR is the reliability factor. Now, this table gives you the allowable bending stress number or AGMA bending fatigue strength SFB dash for some selection of materials with life 10 to the power 7 cycles, surface finish as same as gear, and 99% reliability, and temperature equal to room temperature. Now, you may see in this table different materials are given like steel, and in that different material designations are there. Then cast iron, different class of cast irons are there. Then nodular ductile iron, different class of nodular cast iron are there. Then malleable iron, the bronze, and the heat treatment condition is given either through hardened, flame or induction hardened, carburized and case hardened, nitrided, as cast, annealed, quenched and tempered, sand cast, heat treated, and the minimum surface hardness is given. So, knowing all these, you can get the bending fatigue strength in megapascal from this curve. A range is given. For example, for steel A1, A5 through hardened and minimum surface hardness less than or equal to 180 Brinell hardness, then the bending fatigue strength SFB dash will be in the range of 170 to 230 megapascal. The same table is given in a bigger diagram so that the values can be easily visible. Now, this is a graph which is for through hardened steel gear of grade 1 and grade 2. Knowing the hardness in Brinell or the Brinell hardness and knowing the grade of the steel, whether it is grade 1 or grade 2, you can find the SFB dash. For example, if the hardness is 250 BHN and the grade is 1, then its bending fatigue strength will be this one. But if it is grade 2, then you see there is an appreciable increase in the SFB dash. Now, with the increase in hardness, the SFB dash increases. Now, if the hardness is 350, then the strengths are this and this one depending on the grade of the steel. Now, in place of this graph, you can also use these equations. This is the equation for grade 1 and it is SFB dash is equal to 0.533 HB, the Brinell hardness number of the material, plus 88.3 megapascal. So, by substituting the Brinell hardness number of the material, you may get the SFB dash. Similarly, for grade 2, you have SFB dash is 0.703 HB plus 113 megapascal. Now, in the data books, you may get other tables and figures which can be used to determine the SFB dash. Now, the different modifying factors, the bending fatigue strength modifying factor, the first one is the life factor KL. KL. The KL can be obtained from this figure where on the x-axis is the number of load cycles. That means for which life you want to make your gear. For 10 to the power 7, as SFB dash is for 10 to the power 7, and so for 10 to the power 7 the value of KL is 1. Value of KL is 1 for 10 to the power 7. Now, if life required is less than 10 to the power 6, then the factor, the KL will be more than 1. More than 1 means your SFB is equal to KL SFB dash. So, if you want to design your component for 10 to power 4 number of cycles and the data is available for 10 to power 7 number of cycle, so the strength which you will get will be more than this SFB dash, because for 10 to power 4 number of cycles the value of KL is more than 1. But if you want to design your component for life more than 10 to power 7, for which the value of SFB dash is given, then you will be somewhere here and the value of KL will be less than 1, and in that case your SFB will be less than SFB dash. Well, so depending on the different type of materials, like for 400 HB you will use this curve, for case carburized you will use this curve, and the formulas are also given. Directly you can use the formula, that means KL is 9.4518 multiplied by N, the life for which you want to design. So, if your material steel is 400 HB and the life required is 10 to power 4, then just substitute here 10 to power 4 and get the value of KL. So, for different type of materials different curves are there and you may use them or directly formula to get the value of KL. Now, the temperature factor is equal to 1 up to temperature 120 degree centigrade, and for above you will use the formula 273 plus T temperature in degree centigrade divided by 345. So, we got the factors KL, KT and KR. KR is the reliability factor which can be determined from a table of reliability or a empirical formula which gives the value of reliability, knowing the reliability factor, knowing the reliability for which you want to design the component. So, now knowing the value of SFB, knowing the bending fatigue stress which is acting either in the terms of ST or in the form of sigma B, now you can get the factor of safety. Okay. For safe operating, it is the designer's responsibility to specify a material that has an allowable bending stress or strength. This will be strength greater than the computed stress due to bending. That means the value of this ST or sigma B should be less than the strength of the material. Now, to make this inequality into equality, you have to multiply the left side by a number which is called the factor of safety for bending or for fatigue. So, you can say this as NF or NB, factor of safety due to bending or factor of safety due to the fatigue, and that will be SFB, that means fully corrected strength of the material of the gear, divided by the bending stress number or the bending stress which is acting on the material, and this is also the corrected value by applying all factors. The factor of safety may be used to account for following, that is uncertainties in the design analysis, uncertainties in material characteristics, uncertainties in manufacturing tolerances. It may also be used to provide an extra measure of safety in critical applications. No general guidelines are published and designers must evaluate the conditions for each application. Now, we know that on the gears the mode of failure are of two types: the fatigue fracture due to fluctuating bending stresses at the root of the tooth, which we studied just now. The next stresses which acts is the surface fatigue or the pitting of the tooth surfaces. That means due to contact between the two teeth, there will be contact stresses and they are varying nature, dynamic nature, and therefore there will be surface fatigue phenomena. Materials do not exhibit an endurance limit for repeated surface contact stresses. Now, the surface contact stresses on the gear were derived from a Hertzian contact stress which acts between the two cylinders of diameter equal to d1 and d2. So, in this figure, two cylinders are given. The first cylinder is having diameter d1, the bottom one is having diameter d2, and the length of the cylinder is L. Now, initially when there is no any load, then there will be a line contact between these two cylinders. Now, when a load is applied, due to very small contact area, that is only a line, very high contact stresses develop at the vicinity or at the contact, and those are shown here. The distribution is something like this, and the line contact converts into an area contact with width equal to 2b. This width equal to 2b and length equal to length of the cylinder L. So, earlier there was a line contact. Due to application of load and very high contact stresses, the line contact converts into the area contact with area equal to 2BL, and the stress distribution is shown by this very high contact stresses X. Now, two bodies with curved surfaces pressed together, point or line contact changes to area contact. Point means when there will be spheres in contact, then there will be point contact, and when cylinders are in contact, then there will be a line contact initially. Stresses developed are three-dimensional, called contact stresses or Hertzian stresses, and the examples are wheel rolling on rail, mating gear teeth, and rolling bearings. And the mating gear teeth are shown in this figure. The contact is at this point, and the force is acting along this. Okay, this gear is applying force in this direction on this gear, and this is applying in this direction on the bottom gear. Well, and it can be assumed that the curved surface at the point of contact is just similar to these two cylinders. Okay. So, the analogy was taken between the contact stresses which act on the cylinder and the contact stresses which acts on gear tooth in contact. Now, single tooth contact, that means gear tooth is there and there is a single tooth contact. The instantaneous contact point velocity of gear and pinion are vectorically denoted by Vg and Vp. Vg and Vp. When the contact is at pitch point, then these two will be same and their component along the common normal at the point of contact will be Vgn, and that will equal to Vpn. Vg subscript represents the gear and P subscript represents the pinion, and N is the normal direction. The component along the tangential direction tangent to the point of contact is Vpt is equal to Vgt. Now, when the contact is at pitch point, then these two components will be same, but when contact will be other than pitch point, then these two values will be different, and the difference of these two gives us the sliding velocity. Sliding velocity between the two gears. So, it is clear that when the contact will be at the pitch point, the sliding velocity will be 0 because Vpt is equal to Vgt, but when the contact is other than pitch point, then there will be sliding velocity, and this sliding velocity will be proportional to the distance of contact from the pitch point. As the contact will be farther from the pitch point, the sliding velocity will be more, and the sliding velocity is useful in the lubrication of the gear. If if sliding velocity is 0, there may be a chance of loss of lubrication, and it is dangerous. Okay. So, if the contact is at the pitch point, the sliding velocity is 0, the tooth relative motion is of pure rolling. At all other contact points, the relative motion is one of the pure rolling and sliding. The sliding velocity is directly proportional to the distance between the pitch point and the point of contact. The maximum sliding velocity occurs with contacts at the start and end of the engagement, because at that time the point of contact is farthest from the pitch point. Gear teeth with longer addenda have higher sliding velocities than gears with shorter addenda. Now, the complex stresses within the contact zone cause surface and subsurface fatigue failures. That means at the contact point, the complex stresses will develop, and that may cause the surface and subsurface fatigue failure. Pitting occurs only after a large number of repeated loading, mainly in the vicinity of the pitch point, because at that point the sliding velocity is 0, and so there is a chance of breakage of the lubricant. Now, Buckingham adopted the Hertz contact stress equation for a pair of gear teeth. He treated a pair of gear teeth as two cylinders of radii equal to radii of curvature of the mating involutes at the pitch point. Let us see. And radius of the second cylinder is R2, then the radii of the cylinders are taken to be radii of curvature of involute tooth form of the mating teeth at the point of contact. Let this is the point of contact, then at this point of contact the gear tooth have curvature, this one and this one. Now, if the radius of curvature of these surfaces are taken as for this surface, if the radius of curvature is taken as the radius of the first cylinder R1 and the radius of curvature of the surface of another gear tooth which is under engagement and the point of contact is C, then the radius of curvature of this surface will be R2. So, this R2 is this one and this R1 is this one. So, the cylinders are replaced by radius of curvature of the surfaces of the gear tooth under engagement at the point of contact C. This is again shown, this is the point of contact, and the surfaces of the gear tooth are this one at the point of contact. The radius of curvature is R1 and R2. Okay. So, this is shown here. This Wn is acting along the pressure line. This is the point of contact at the pitch point. This is the pitch point P. So, one of the curve is this one, another curve is this one of the cylinder, and the radius is this one up to the base circle. The base circle is passing through this. This is the line joining the center of rotation. center of rotation. Okay. So, this is the radius of the cylinder, and this is the normal load which is acting on it, and this normal load is shown here. This is Wt, this is Wn. Now, for the cylindrical contact stresses, stress is for the case of cylinder is sigma x is given by this one. That means the stress in this direction is given by this formula, where z is the distance in the z direction, sigma y by this formula, sigma 3 or sigma z by this formula. Okay, and sigma z is the stress acting in this way. Okay. Now, after substituting the value of B, this is 2B. 2B is given by this equation, which is equal to under root 2F, the force which is acting on it, divided by pi L 1 minus nu1 square. It is the Poisson ratio of first cylinder. E1 is the Young's modulus of the first cylinder, and nu2 is the Poisson's ratio of the second cylinder, and E2 is the Young's modulus of the second cylinder. D1 is the diameter of the first cylinder, and D2 is the diameter of the second cylinder. And the maximum pressure, this maximum pressure P maximum, which acts, is given by the formula 2F divided by pi BL. Now, substituting the value of B, you can get the maximum pressure or the maximum stress which is developed at the contact point. Now, this formula we will use with the substituted value of F, substituted value of this D1, nu1, this all E1 for the case of gear. This is for the cylinder, and for the case of gear, what we will do is this F will be substituted by Wn, and Wn is given by Wt cos phi. Wt cos of the phi, phi is the pressure angle, by, and D, capital D by 2R, L by phase width F. With these changes, we can substitute the value of B, replacing P maximum by the Hertzian contact stress for the case of gear, and that formula is given by this sigma c square. The Hertzian contact stress is equal to which will act between the two gears at the pitch point, two gear tooth. At this point, the Hertzian contact stress is given by Wt divided by pi f cos phi, then 1 upon R1 plus 1 upon R2 divided by 1 minus nu1 square divided by E1 plus 1 minus nu2 square divided by E2. Okay. Now, for our case, the value of this R1 is this distance. Okay. And this is equal to D1 divided by 2. D1 divided by 2 is the pitch circle radius of this one. D1 divided by 2, this distance. Okay. And this angle is phi. So, the radius of equivalent cylinder, R1 will equal to D1 divided by 2 sine of the phi, this distance, PA, capital PA. This is actually capital PA, capital PA. Similarly, capital PB, this is your D2 divided by 2 or D gear divided by 2, this will be D pinion divided by 2, this will be D gear divided by 2, this distance, this angle is phi, and so this distance is actually R2, and R2 is D2 sin phi divided by 2. So, 1 upon R1 plus 1 upon R2, which is used in this formula, is given by this one. After substitution, we got the Hertzian contact stress in the gear from this formula. In this formula, this dP, capital dP is the pitch diameter of the pinion, nu p is the Poisson's ratio of the pinion material, nu g is the Poisson's ratio of the gear material, EP is the modulus of elasticity of the pinion material, EG is the modulus of elasticity of the gear material, and mg is the gear ratio which is given by number of teeth on the gear divided by number of teeth on the pinion. Now, in this formula, if you see this term is dependent on the material, nu p, Poisson's ratio and the elastic, and it is combined and it is given the name elastic coefficient Cp, and Cp is given by under root 1 divided by pi and the term related to the material property in this equation. So, your contact Hertzian contact is Wt divided by dpf 1 divided by sine by mg plus 1. Now, elastic coefficient Cp for spur gear is obtained from pinion material is steel and gear material is steel, then it is 191 under root megapascal. In the equation of contact stresses, we have this term is taken as I cos phi t sin phi t divided by 2 mg divided by mg plus 1. This is called the geometry factor I for the pitting resistance, and the I is given by this for the external gear, and for internal gear it will be mg divided by mg minus 1, and mn is equal to 1 for the spur gear, this mn. So, we have Cp given by this. AGMA has used these modifying factors similar to the your factors used for bending fatigue, Kv, Ko, Km and Ks. We have Cv, Co, Cm and Cs, and they are determined very much similar to the previous ones. So, the AGMA surface fatigue strength can be determined from the data sheets, data books. You get SFS dash, and it is modified with the help of modifying factors, the life factor, the hardness correction factor, temperature factor and the reliability factor. These are the tables and graphs to get the SFC dash is the contact fatigue strength obtained from the literature, that is corrected with the help of the correction factors CL. Then we will study in our next class. Thank you.
Hello and welcome to this piece of literary snippet. We usually know William Shakespeare as the most revered figure in the history of English literature. But we often tend to forget that he has also been one of the most hated figures in literature. And here I am not talking only about those boys and girls who have to memorize long sections from Macbeth or King Lear or Julius Caesar before they can go and sit for their school or college exams. But I am also talking about people who are themselves quite famous authors. Tolstoy, for instance, considered the writings of Shakespeare to be, and I quote, crude, immoral, vulgar, and senseless. George Bernard Shaw absolutely loathed Shakespeare, as he did Homer. But perhaps no other criticism about Shakespeare is more damaging than the one which says that Shakespeare is a marvelous storyteller, provided someone has told him the story earlier. Now, this piece of criticism is particularly damaging because it is true. None of Shakespeare's plays contain any original story whatsoever. They are all written using pre-existing materials, pre-existing stories. Now, does that diminish the stature of Shakespeare as a dramatist? Well, I'll leave that for you to decide. See you in the next episode of Literary Snippets.